So far with KSP, we've been talking about how things dissolve when they're going into pure water. So I'll remind you of a problem we have talked about before. And this is silver chromate. So silver chromate is only slightly soluble. Normally you would have been calling it insoluble, but even things that are insoluble has a few ions that dissolve depending on how insoluble they are. In this case, remember when it comes to salts dissolving, salts are ionic compounds. So ionic compounds are always going to have a cation and an anion. So you'll be able to figure out what the cation is because the only positive polyatomic ion we have is ammonium. So if it doesn't start with ammonium, then the first element there is going to be your cation. In this case, we have 2 silver plus 1 ions dissolved in solution. Remember, silver is the one that we confuse the most often, so don't forget that it's plus 1, because otherwise it's going to be hard for you to remember that chromate is minus 2. So they're going to give you a KSP for silver chromate of 9.0 times 10 to the minus 12. Remember that if we were in water with 3 ions, KSP would be 4x to the third. That's our pattern. So in order to figure out the solubility or how the concentration of each ion, I'm going to solve this, which would be 9.0 times 10 to the minus 12 divided by 4. And then I'm going to take the cubed root of that. And I will get a value for x of 1.31 times 10 to the minus 4. So 1.31 times 10 to the minus 4. So let's see. 0.000131 moles of silver chromate will dissolve in 1 liter of solution. Therefore, at equilibrium, the concentration of chromate ions is 1.31 times 10 to the minus 4, because only 1 piece comes on, but twice as many silver for 2.62 times 10 to the minus 4 molar silver ions. Okay, that's what we've learned so far. Now we're going to talk about what a common ion problem would look like. And actually, believe it or not, common ion problems are more likely. So a common ion problem would say, how much silver chromate will dissolve in a solution that is 0.010 molar potassium chromate. So they're called common ion problems because you have to figure out which ion is common. In this case, the ion that is common is obviously chromate. So when we do our ice chart, we still don't care about the solid. Solids concentration are considered constant, so they do not take place in equilibriums. We started off with no silver, but Let's look at this. We got to be careful. There's one chromate. So the concentration of chromate ions is 0.010 molar also. But if they asked you about potassium ions, the concentration of potassium ions, because you're going to get two ions for each one piece of potassium chromate that dissolves. But they asked us about chromate, so 0.010 molar is going to be what we start with. You're going to get two pieces of silver and one piece of chromate. So at equilibrium, the concentration of silver will be 2x. The concentration of chromate will be 0.010 plus x. So KSP is still going to be concentration of silver ions, don't forget your squared, times the concentration of chromate ions. And they gave us the KSP of 9.0 times 10 to the minus 12. So I'm going to replace silver with 2x. And chromium is 0.010 plus x. But we're going to do the same thing that we did when it came to weak acids and bases. We're going to say the contribution to 0.010 from this x is going to be very, very small, because this is 10 to the minus 12. So we're going to simplify this problem to be 4x squared times 0.010 equals 9.0 times 10 to the minus 12. That's how we make this problem more consumable and a little bit easier. So don't forget that we can ignore the contribution made by x. So 4x squared equals 9.0 times 10 to the minus 10. We'll divide by 4 and then take the square root of it. And the value for x is 1.5 times 10 to the minus 10. That's the value for x. So they're asking you how many pieces of silver chromate. That means that, here, let's write it out. 1.5 times 10 to the minus 10 moles of silver chromate will dissolve in 1 liter of solution that already has potassium chromate in it. So the only thing that is new to this type of problem is the fact that we do not start at 0 for all of the ions. And we need to remember that we can ignore this. Otherwise, the problem becomes pretty complicated and you would be doing some serious math. Okay, does that make sense to everybody? Does anybody have any questions? Okay, let's do one more together then, and then I'll let you guys, oops. So another problem states, calculate the solubility of solid calcium phosphate with a KSP of 1.3 times 10 to the minus 32 in a 2 molar sodium phosphate solution. 0.2 molar. Okay, we actually did calcium phosphate when it was in a solution of just water. So you can look back over the notes if you don't remember how, but let's run through here and we're going to do an ice chart. So it is slightly soluble. That means that for every 1 piece of calcium phosphate that dissolves, I'm going to get 3 pieces of calcium ions to dissolve and 2 pieces of phosphate ions to dissolve. This time my common ion is phosphate, so I'm going to have some phosphate floating around. In this case, every 1 piece of sodium phosphate that dissolves gives me 1 piece of phosphate ions. So we're going to start with 0.2 molar, 0. These are our initial conditions. C stands for change. We still don't care about the solid. This is going to be plus 3x. This is going to be plus 2x. At equilibrium, this is going to be 3x. This is going to be 0.20 plus 2x. Let's go and plug that into our KSP expression. KSP, until you get comfortable, I suggest you do all the steps, is the concentration of calcium cubed times the concentration of phosphate squared. And that's going to equal the KSP, which is 1.3 times 10 to the minus 32. Now we'll replace calcium with 3x and phosphate with 0.20 plus 2x squared. Now again, this is a pretty complicated problem, so let's just ignore this guy and let our problem become 27x to the third times 0.2 squared equals 1.3 times 10 to the minus 32. So I'll go through this step by step. 27x to the third equals, we're going to take 1.3 times 10 to the minus 32nd divided by 0.2 squared and get 3.25 times 10 to the minus 31. Now we'll divide by 27. And we'll take the cubed root of that. So my answer becomes 2.297 times 10 to the minus 11. This is how many moles of calcium phosphate will dissolve in 1 liter of solution that already has phosphate ions dissolved in it.